Hello students, let us now discuss on the topic basic concept of organic molecules. Introduction. Recently, organic compounds have been denoted as compounds containing a significant amount of carbon in any of them. So all organic compounds contain carbon. Hydrogen is constituent element of most of the organic compounds, and many of them contain oxygen. Some of them contain nitrogen, but a few of them contain sulfur, phosphorus, etc. Now we will discuss about the bonds involved in the formation of organic compounds. Types of chemical bonds of organic compounds. It can be noted that the bonds formed in organic compounds are exclusively covalent bonds. It can be reminded that covalent bonds are formed by sharing of electrons among the combining atoms. The two main types of covalent bonds are sigma and the pi bonds. A sigma covalent bond is formed by linear or end-to-end overlap of two atomic orbitals along their internuclear axis. A pi bond is formed by parallel or side-by-side overlap of two atomic orbitals. Orbitals are maximally overlapped in the formation of sigma bond. The electrons which are involved in the formation of sigma and the pi bonds are known as sigma and the pi electrons respectively. Pi electrons are more loosely held than the sigma electrons. Electronic configuration of carbon atom. It is understood that atomic number of carbon is 6 and that therefore it has 6 electrons. So 2 electrons are in K cell while 4 electrons are in L cell. The subcell of K cell is S while those of L cell are S and P. Orbitals of P subcell are Px, Py and the Pz. So ground state electronic configuration of carbon atom is 1 S2, 2 S2, 2 Px1, 2 Py1, 2 Pz0. Hybridization of orbitals of atom. Mixing of pure orbital producing a set of new equivalent orbitals is known as hybridization. This process, which takes place in valence shell, may or may not involve all of its orbitals. sp3 hybridization of carbon. In the valence shell of carbon atom, which is L cell, there are 4 electrons, due to which the valency of carbon is 4. In the ground state, S orbital of L cell has 2 electrons, but in this cell, while 1 electron is present in each of Px and the Py orbitals, Pz orbital is empty. When such carbon atom is to combine with hydrogen, there would be formation of compound of formula CH2 from overlap of Px and the Py orbitals with 1 s orbital of a hydrogen atom in each case. However, the simplex stable compound of carbon and hydrogen is known to be methane, which has 4 identical carbon to hydrogen bonds. The formation of a molecule of methane can be narrated in the following way. In a process known as excitation of electron, which requires energy, one of electrons of s orbital of L cell is promoted to Pz orbital. The source of energy is light or heat of the surrounding and the carbon atom is in excited state. They mix with Px and the Py orbitals, producing 4 equivalent orbitals which are known as sp3 hybrid orbitals or simply sp3 orbitals. Although a hybrid orbital has a larger lobe and a smaller lobe, only the former participates in the formation of covalent bond. These hybrid orbitals have same shape. Each of these hybrid orbitals contains one electron and possesses 25% S character and 75% P character. These hybrid orbitals contain same energy. However, they differ in orientation in space since their axes are directed toward four corners of a regular tetrahedron wherein carbon atom is in its center. This makes any interorbitals angles to be 109 degrees and 28 minutes. As such orientation allows staying of orbitants at the farthest gap possible, repulsion among electrons has been reduced, thereby favoring the tetrahedron arrangement of orbitals. It is known that a molecule of methane is formed by bonding four hydrogen atoms with a carbon atom. A sigma bond is formed by overlap of a sp3 hybrid orbital with one s orbital of a hydrogen atom, and thus in methane there are four sigma bonds, a hydrogen atom being located in each of the four corners of the regular tetrahedron. Next, sp2 hybridization of carbon. In bonding of a carbon atom with three other atoms or groups, it always uses sp2 hybridization. S orbital and the two of the p orbitals of the L shell of carbon atom in excited state mix, producing sp2 hybrid orbitals, which are equivalent ones. Its shape is same to that of sp3 hybrid orbital and thus has 33% S character and 67% P character. In orientation, each of their axis directs to a corner of an equilateral triangle, and thus the three orbitals lie in the same plane. In ethylene, since each of the carbon atom is bonded to three other atoms, hybridization of orbital undergone is sp2. The four carbon to hydrogen bonds of ethylene are sigma covalent bonds. One of the covalent bonds of the double bond is sigma bond, which is formed by end-to-end overlap of a hybrid orbital of each carbon atom. But pi bond of the double bond is formed by side-by-side overlap of two pz orbitals. The two carbon atoms and the four hydrogen atoms being land in the same plane. The carbon to hydrogen bond length of methane, ethane, and ethylene is same, with a value of 1.09 angstrom. Next, sp hybridization of carbon. In the bonding of a carbon atom with other two atoms or groups, it always uses sp hybridization. The carbon atom is in excited state as narrated previously, and the S and the one of the p orbitals mix, forming two sp hybrid orbitals. The shape of sp hybrid orbital is identical to that of sp2 hybrid orbitals, but they orient at 180 degrees to each other. The axis of these hybrid orbitals, 2py and 2pz orbitals, orient at right angles to each other. In acetylene, the two carbon atoms are bonded by a triple bond of not all identical covalent bonds. Out of this, one is sigma covalent bond and the two are pi bonds, one formed by two py orbitals of the two carbon atoms and another formed by their two pz orbitals. A hydrogen atom is bonded to each of these carbon atoms with the formation of a sigma covalent bond. Next, hybridization of nitrogen. The atomic number of nitrogen is 7, and a nitrogen atom has one more electron than a carbon atom. Thus, it is certain that one s and the two s orbitals of nitrogen have 2 electrons in each, while each of its 2 px, 2 py, and the 2 pz orbitals has 1 electron. Thus, the valence shell has 5 electrons, rendering valency of nitrogen to be 3. Like carbon atom, it undergoes sp3, sp2, and the sp hybridization. Next, sp3 hybridization of nitrogen. In the bonding of a nitrogen atom with 3 other atoms or groups, it always uses sp3 hybridization. Yes, px, py, and the pz orbitals of L shell mix, producing 4 hybrid orbitals. The shape is similar to that of sp3 hybridized orbitals of carbon, but one of the sp3 hybrid orbitals of nitrogen has a pair of electrons and does not take part in bonding. In ammonia, each of the hybrid orbitals of nitrogen having 1 electron forms a sigma bond with a hydrogen atom. Next, sp2 hybridization of nitrogen. In the bonding of a nitrogen atom with 2 other atoms or groups, it always uses sp2 hybridization. S orbital and the 2 of the p orbitals of L shell mix, producing 3 hybrid orbitals, but one of them accommodates a pair of electrons. In imine, each of the carbon and the nitrogen atoms forming double bond has been sp2 hybridized. Double bond between carbon and the nitrogen consists of a sigma bond and a pi bond formed by their hybridized and the pz orbitals respectively. Next, sp hybridization of nitrogen. In the bonding of a nitrogen atom with 1 atom or group, it always uses sp hybridization, which is mixing of s orbital with 1 of the p orbitals of L shell. Of the 2 new hybrid orbitals formed, one has a pair of electrons. In hydrogen cyanide, both carbon and the nitrogen atoms are sp hybridized. Triple bond between carbon and the nitrogen has a sigma bond and 2 pi bonds, one formed by py orbitals and the another formed by their pz orbitals of these atoms. Next, hybridization of oxygen. Atomic number of oxygen is 8, and so valence shell has 6 electrons accommodating a pair of electrons in each of s and the px orbitals and the 1 electron in each of py and the pz orbitals. But it undergoes only sp3 and sp2 hybridization. Among the 4 sp3 hybrid orbitals, 2 contain a pair of electrons in each, while the remaining 2 contain 1 electron in each. In a water molecule, each of the hybrid orbitals of oxygen having 1 electron overlaps with s orbital of a hydrogen atom, forming a sigma bond. Thus, it is conspicuous that for bonding of an oxygen atom to other 2 atoms or groups, it uses sp3 hybridization. As 2 of its sp2 hybrid orbitals contain a pair of electrons in each, only one of them contains 1 electron. This hybridization is used when oxygen is bonded to other 1 atom or group, as in formaldehyde. Next, hybridization of sulfur and the phosphorus. As valence or M shell of sulfur has 6 electrons, it adopts sp3 and sp2 hybridization as done by oxygen. But phosphorus can have expanded octet of 10 electrons in the M shell, as each of the sp3 hybrid orbitals and the d orbital in M shell of phosphorus has 1 electron. It forms a double bond with 1 oxygen atom and 3 sigma bonds with 3 oxygen atoms as in phosphate. Examples of phosphate-containing organic compounds are nucleotides, phospholipids, and the glucose 6-phosphate, etc. Next, homolytic and the heterolytic fissions. We know that an organic reaction takes place with at least breaking of 1 covalent bond and the formation of 1 covalent bond. The breaking of a sigma covalent bond takes place in 2 ways, such as homolytic and heterolytic fissions. In homolytic fission of a covalent bond, each of the 2 products receives 1 electrons of the bonding electrons. The products form being free radicals. It is known as radical fission. In heterolytic fission of a covalent bond, the bonding electrons are taken by more electronegative product. As one product is positively charged while another one is negatively charged, this reaction is known as ionic fission. Most of organic transformation undergo with heterolytic fission. Next, electrophile and nucleophile. It is known that chemicals causing reactions are known as reagents. The types of reagents are electrophile and the nucleophile. An electrophile is a reagent that receives a pair of electrons during the reaction. Since electrophiles are electron-loving, they attack the regions of high electron density. Nucleophiles are nucleus-loving reagents. Thus, a nucleophile is a reagent that donates a pair of electrons during the reaction. Now we are coming to the conclusion. For the bonding of carbon atom, 2 other 4, 3 and the 2 atoms or groups, it always uses sp3, sp2 and sp hybridization respectively. However, nitrogen atom always use sp3, sp2 and the sp hybridization for bonding to other 3, 2 and 1 atoms or groups respectively. On the other hand, oxygen always uses sp3 and sp2 hybridization for bonding to other 2 and 1 atoms or groups respectively. Oxygen does not adopt sp hybridization. Sulfur undertakes hybridization as done by oxygen. Phosphorus can have expanded octet of 10 electrons in M shell. The bonds of organic compounds are mostly covalent bonds. An organic reaction takes place with at least breaking of 1 covalent bond and the formation of 1 covalent bond. The breaking of sigma covalent bond takes place in 2 ways, such as homolytic and the heterolytic fissions, which produce free radicals and the ions respectively. The number of products formed being 2 in each case. An electrophile carries out reaction by receiving a pair of electrons, while a nucleophile does it by donating a pair of electrons.